All right, today we're going to be looking at section 3.1, introducing derivative. The big takeaway here is that you want to know that the derivative of the function is going to be the slope of the line at a point, also known as the instantaneous rate of change. And so you can see some figures. A parabola, slope is going to be different on each side. And it's changing. It's not consistent as if it was a linear function, but as you go along this line, the slope is changing at different points. And the slope, again, the slope of the tangent line, instantaneous rate of change are the same. So here we're just reminding you of the average velocity function. Looks just like the slope formula. The instantaneous rate of change, the formula is just the limit as we approach, as we get closer and closer to that point. So you have 2 points, gives you a secant line, but as these points get closer and closer together, the limit as those points get closer and closer together is the slope of the tangent line, which is the instantaneous velocity. And so you see some examples, and they're breaking down the definition, showing you how to do it step by step. So take some time, read through those. Again, they're talking about the tangent line. Again, the tangent line is just the slope of the secant line. So given 2 points, you will take the slope, and that will be the slope of that secant line. And then if you take the limit again, you get the instantaneous rate of change. And so sometimes we'll be asked to write the equation of the tangent line, which will just take that formula, find the limit, and then plug in a point. Here we are given the definition. It says rate of change and the slope of the tangent line. So it's just telling you average rate of change over the interval a to x is the slope of the corresponding line. The instantaneous rate of change is the same exact formula. It's just you're taking the limit. So as you get closer and closer together, it says this is also the slope of the tangent line, provided that the limit exists, and it says the tangent is unique through a f of a. So you're going to get a unique equation. And then when you want to write the equation of the tangent line, again, you're going to be using that slope and then using the point A in the f of a to come up with the equation. So here we are given an example using the point 2,3, and given this function, we're going to find the equation of the tangent line of f at this point. And so we go through finding the slope, and then we plug that in and come up with the linear equation. Here we are using the same thing, the difference quotient. Just giving you a different form. So just an alternative definition for rate of change and slope of the tangent line. So this is the difference quotient. Again, it's exactly the same, except we're just using the formula with h, and then we say that the limit as h goes to 0. So as those points get closer and closer together as well. And then you have some examples here, and then it says derivative of a function at a point. So if we want to find the derivative of a function, no matter what the value is, we're following one of the 2 definitions. So we can either do the limit f of x minus f of a as x gets close to a, or we can do the difference quotient, which is f of a plus h minus f of a divided by h as the limit of h goes to 0. And then other than that, we just have some various functions that you get to practice with. Again, finding the instantaneous rate of change, which is the slope of the tangent line, or the derivative at some point. And with that, we're going to jump into my math lab and solve a few problems.